Hello there, you're listening to The Planet's Memory, where time breathes and the Earth remembers. Close your eyes and let your mind drift backward through the endless corridors of time, beyond the reach of recorded history, beyond the memories of humanity itself, into a realm where the very ground beneath your feet was something utterly different from anything you have ever known. Imagine a world so ancient that the continents themselves had not yet taken their familiar shapes, a time when the Earth wore a face so foreign that no living person could recognize it, and upon this strange and distant world, there may have existed something extraordinary, something that challenges everything we think we understand about the origins of life and civilization on our planet. Tonight, we journey together into the deepest shadows of geological time, to a place that existed long before Pangea, the supercontinent you learned about in school, to discover what mysteries might have flourished on an even older landmass, a primordial continent that cradled secrets we are only beginning to whisper about in the quiet halls of science. This is a story that begins before beginnings, a tale that unfolds in the silence between heartbeats of the Earth itself. And as you settle into the gentle embrace of rest, let your imagination travel with me across billions of years to witness the impossible, the forgotten, and the hauntingly beautiful truth about what came before everything we know. The story of our planet begins in fire and chaos, in a cosmic dance of matter and energy that transformed a cloud of dust and gas into the solid ground upon which all life would eventually stand. 4.5 billion years ago, the Earth was born from the same nebula that gave rise to our Sun and all the planets that orbit within our solar system. And in those earliest moments, our world was nothing more than a molten sphere of rock, a hell of liquid stone and volcanic fury that bore no resemblance to the blue and green jewel we know today. The surface was an ocean of magma glowing with the heat of creation itself, and above this infernal landscape, the sky was choked with thick clouds of steam and poisonous gases that blocked out the stars and sun alike. This was a world without water on its surface, without air that any living thing could breathe, without the gentle conditions that would one day allow forests to grow and animals to roam and civilizations to rise and fall. For millions of years, the Earth remained in this state of primordial violence, gradually cooling as heat radiated away into the void of space, its surface slowly hardening into the first solid crust, thin and fragile like the skin forming on cooling pudding. Meteorites and asteroids still bombarded the young planet with relentless fury, bringing with them not only destruction but also the building blocks of life itself, delivering water frozen in ice and organic molecules that would become essential ingredients in the recipe for life. As the bombardment gradually lessened and the surface continued to cool, something miraculous began to happen. The water vapor that had been trapped in the thick atmosphere began to condense and fall as rain. Rain that lasted not for days or weeks but for millions of years. An endless deluge that slowly filled the lowest places on the cooling crust, creating the first oceans, primitive and hostile, but oceans nonetheless. These ancient seas were nothing like the waters we know today, acidic and mineral-rich, constantly churned by violent storms and heated by volcanic activity that continued to reshape the young planet's surface. Beneath these turbulent waters, chemical reactions of staggering complexity were taking place, molecules colliding and combining in ways that would eventually lead to the emergence of the first living things. Though that moment still lay hundreds of millions of years in the future, the solid crust of the Earth was still thin and unstable, broken into countless fragments that floated on the molten rock below like islands of hardened slag on a sea of liquid metal, constantly moving and colliding and melting and reforming in an endless cycle that would eventually give rise to the process we now call plate tectonics. The first true land masses began to form as lighter rocks accumulated and rose above the surface of the primordial oceans, creating small proto-continents that were nothing like the vast continents we know today, but represented the beginning of something new in Earth's history. These tiny land masses were constantly being reshaped by volcanic eruptions and the collision of crustal plates, growing larger as more material accumulated, shrinking again when they were torn apart by the forces moving beneath the surface. For hundreds of millions of years, the Earth's surface remained in constant flux, a dynamic and violent place where nothing remained stable for long, where the concept of a permanent landmass was meaningless because everything was temporary, everything was in motion, everything was in motion, everything was in motion. The atmosphere gradually changed as well, losing much of its original hydrogen and helium to space, while gaining new gases released by volcanic eruptions, nitrogen and carbon dioxide and water vapor, that would eventually create conditions more favorable to life, though oxygen, the gas that most life on Earth now depends upon, was still almost entirely absent. In the darkness of the ancient oceans, far from the harsh radiation of the sun that beat down mercilessly on the barren land, something extraordinary was happening. Within the warm, mineral-rich waters near volcanic vents on the seafloor, where chemicals and heat created conditions unlike anywhere else on the young planet, the first living things were coming into existence. These were not organisms as we would recognize them, not cells with complex structures and genetic material neatly packaged in a nucleus, but something simpler and more primitive, perhaps just self-replicating molecules, chemical systems that could make copies of themselves using the materials dissolved in the water around them. The exact process by which non-living chemistry became living biology remains one of the great mysteries of science, a transition so profound and so unlikely that it seems almost miraculous. Yet it happened here on Earth at least once, and perhaps it happened many times, with countless failed experiments preceding the first successful spark of life. These first living things, emerging perhaps 3.5 billion years ago or even earlier, were microscopic and simple, likely resembling modern bacteria more than any other living thing, though even bacteria today are enormously sophisticated compared to what the first life must have been like. They made their living not from sunlight, which could not penetrate to the depths where they dwelt, but from the chemical energy available in their environment, processing minerals and gases to fuel their metabolism, reproducing by simply splitting in two, passing copies of their genetic material to each daughter cell. For hundreds of millions of years, perhaps even 1 billion years, these simple microbes were the only living things on Earth, and they remained confined to the oceans because the land was still a lifeless wasteland, scoured by ultraviolet radiation that would destroy any living tissue exposed to it. The atmosphere still lacked the ozone layer that now protects the surface from the sun's most harmful rays, making the land utterly inhospitable to life as we know it. But some of these early microbes discovered a new way to make a living, one that would eventually transform the entire planet. But these were rivers without fish, flowing through landscapes without plants or animals, silent except for the rush of water and the howl of wind across empty stone. The movement of the tectonic plates that carry the continents across the surface of the Earth is driven by heat flowing from the planet's interior, and this movement is relentless and inevitable, continuing as long as the Earth's core remains hot. The plates move slowly, just a few centimeters per year, but over millions of years this movement can carry continents across thousands of kilometers, bringing them together in massive collisions or tearing them apart in rifts that become new oceans. Around 2.5 billion years ago, the scattered continents of the early Earth began to come together in one of the first great gatherings of land in our planet's history, forming what geologists call a supercontinent, a single massive landmass that contained most or all of the continental crust that existed at that time. This ancient supercontinent has been given several names by different researchers, but many call it Ur or Valbara, though the exact configuration of these early supercontinents remains uncertain because the geological evidence from such ancient times is fragmentary and difficult to interpret. This first supercontinent, whatever we choose to call it, represented a new chapter in Earth's history, a time when vast areas of land were connected, when mountain ranges pushed high into the sky, where plates collided at the supercontinent's heart, when coastlines stretched for thousands of kilometers without major interruptions. The climate of such a massive landmass would have been different from anything we see today, with the interior far from any ocean, likely creating vast desert regions where almost no rain fell and temperatures fluctuated wildly between baking heat and freezing cold. The formation of a supercontinent also affects the oceans, concentrating them into a single massive body sometimes called a superocean, and this too has profound effects on climate and ocean circulation, changing the way heat is distributed around the planet, altering weather patterns on a global scale. But for all its importance to the physical evolution of the Earth, this first supercontinent was still a dead place as far as we know, home to no life beyond perhaps some hardy microbes living in protected environments near water sources, because complex life had not yet evolved, and plants had not yet colonized the land. While the first supercontinent was forming and breaking apart in the endless dance of plate tectonics, life in the oceans was undergoing a revolution that would have consequences impossible to overstate. For hundreds of millions of years, the oxygen produced by photosynthetic bacteria had been reacting with dissolved iron and other chemicals in the ocean and in exposed rock on the continents, preventing it from accumulating in the atmosphere. But eventually, around 2.5 to 2 billion years ago, something changed. The Earth's supply of easily oxidized materials had been largely used up, and oxygen began to accumulate in the atmosphere for the first time. This event, known as the Great Oxidation Event or the Oxygen Catastrophe, was one of the most dramatic changes in Earth's history, transforming an atmosphere that had been essentially oxygen-free into one containing significant amounts of this highly reactive gas. For the many microbes that had evolved in an oxygen-free world, this change was indeed a catastrophe because oxygen was toxic to them, reacting with their cellular components and destroying the chemical machinery they used to make a living. Many species of microbes must have gone extinct during this time, unable to adapt to the new conditions, while others retreated to environments where oxygen could not reach, places like deep ocean sediments and the guts of animals where they continue to live today as anaerobic bacteria. But for other organisms, oxygen represented an opportunity, a rich source of chemical energy that could be exploited by any organism that evolved the ability to use it safely. Oxygen is a powerful electron acceptor, and organisms that learn to use oxygen in their metabolism could extract far more energy from their food than was possible with any other metabolic strategy. This led to the evolution of aerobic respiration, the process that most complex life on Earth uses today, burning sugars with oxygen to produce energy much more efficiently than any other method. The availability of this new, more efficient energy source may have been one of the key factors that eventually allowed complex multicellular life to evolve, because complex organisms with many different types of specialized cells require a lot of energy to build and maintain. Energy that may simply not have been available before oxygen became abundant in the atmosphere. The increase in atmospheric oxygen also led to the formation of the ozone layer high in the atmosphere, where oxygen molecules are broken apart by ultraviolet radiation and recombine into ozone, which in turn absorbs ultraviolet radiation, protecting the surface from the sun's most harmful rays, and eventually making it possible for life to move onto the land without being immediately destroyed by radiation. The world that emerged from the Great Oxidation Event was fundamentally different from anything that had come before. A world with an oxidizing atmosphere, with an ozone layer, with the potential for much more complex and energetic life. Yet life remained microscopic and simple for a very long time after this transition, confined to the oceans and following what to our eyes would seem an almost incredibly slow pace of evolution. For more than 1 billion years after the Great Oxidation Event, the Earth's oceans were dominated by simple, single-celled organisms, bacteria and archaea, and the first eukaryotic cells, which had evolved a more complex cellular structure with a nucleus and other specialized compartments. This enormously long period, stretching from about 2 billion to around 1 billion years ago, is sometimes called the boring billion because so little seems to have happened, at least in terms of obvious evolutionary innovation. But appearances can be deceiving, and during this time, important changes were occurring that would set the stage for everything that followed. Changes in the chemistry of the oceans, in the genetic complexity of organisms, in the relationships between different species as some began to live inside others in mutually beneficial partnerships. The continents, meanwhile, continued their endless waltz across the face of the Earth, driven by the heat engine of the planet's interior, coming together and breaking apart in cycles that play out over hundreds of millions of years. After the first supercontinent broke apart, the fragments drifted away from each other for a time, carried on their tectonic plates across the globe, opening new oceans between them. But the force that pulls continents apart is eventually balanced by forces that push them back together, and the fragments inevitably begin to converge again, pulled toward each other by the movement of the mantle below, colliding in slow-motion impacts that push up mountain ranges and weld the continents into new configurations. Around 1 billion years ago, the scattered continents of the Earth began to come together once more, forming a supercontinent that geologists have named Rodinia, from a Russian word meaning homeland or birthplace. This was not the first supercontinent as we have seen, but it is the oldest one for which we have fairly good evidence about its configuration, because rocks from this period are more common and better preserved than rocks from earlier times. Rodinia was a massive landmass, probably comprising almost all of the continental crust that existed at the time, stretching from pole to pole or nearly so, with what would eventually become North America near the center, surrounded by the other continents arranged in a configuration quite different from anything we would recognize today. The assembly of Rodinia was a slow process that took perhaps 200 million years or more. As smaller continents and fragments collided and merged one after another, their edges crumpling and rising up to form great mountain ranges, some of which were eventually eroded away completely, while others still exist today as the worn-down roots of ancient peaks. The formation of Rodinia would have had profound effects on the Earth's climate, just as the formation of any supercontinent does, because having all the land concentrated in one place changes ocean currents, changes the distribution of rainfall, changes the amount of weathering that occurs on the continents, and therefore the amount of carbon dioxide removed from the atmosphere. Life during the Rodinian period remained simple and microscopic for most of the time that this supercontinent existed, though this was also the time when the first multicellular organisms began to appear. Simple things at first, not much more than colonies of identical cells, but representing a crucial step toward the complex life that would eventually fill the oceans and colonize the land. The oceans were still dominated by bacteria and single-celled eukaryotes, and the land remained barren, a lifeless expanse of rock and sand and gravel, swept by wind and carved by water, but supporting no plants, no animals, no visible life of any kind. It is hard for us to imagine such a world, so different from the vibrant, life-filled planet we know, but for most of Earth's history, this was the normal state of affairs. A planet where life existed but was hidden away in the oceans, invisible to any observer standing on the shore. A world of stone and water and sky, without the green of forests or the songs of birds or the movement of animals. Rodinia, like all supercontinents before it and since, was not stable, and the same tectonic forces that had brought it together eventually began to tear it apart. Starting around 750 million years ago, rifts began to open in the supercontinent, cracks in the crust where the land was being pulled apart by forces deep within the Earth, creating valleys that gradually grew wider and deeper, eventually filling with water as the ocean flooded in. This breakup of Rodinia was not a single event, but a long, drawn-out process that took hundreds of millions of years, with different pieces breaking away at different times, drifting off to begin their own journeys across the globe. The breakup of a supercontinent has profound effects on the Earth's climate because it changes ocean circulation patterns, creates new coastlines where weathering can remove carbon dioxide from the atmosphere, and generally makes the planet more hospitable to life by creating a more moderate, less extreme climate compared to the harsh conditions that prevail in the interior of a supercontinent. But the breakup of Rodinia coincided with one of the most dramatic and mysterious events in Earth's history, a time when the planet may have become almost entirely frozen, covered from pole to pole with ice and snow, a frozen world where even the oceans were covered with ice kilometers thick, blocking out the sun and bringing the planet closer to lifelessness than it has ever been before or since. This hypothetical period is called Snowball Earth, and the evidence for it comes from geological formations found on every continent, rocks that appear to have been formed by glaciers at a time when they were located near the equator, which should be the warmest part of the planet. If the Earth really did freeze over completely or nearly so, it would have been a catastrophe for life, with only a few hardy microbes surviving in whatever warm spots remained, perhaps near volcanic vents on the ocean floor, or in pockets of liquid water beneath the ice. The cause of such a dramatic freezing is still debated, but it may have been connected to the breakup of Rodinia, because the creation of new coastlines and mountain ranges would have accelerated the weathering of rock, removing carbon dioxide from the atmosphere and reducing the greenhouse effect that keeps the planet warm. The Snowball Earth periods, there may have been more than one, probably lasted for millions of years each, with the planet locked in a frozen state that seemed almost impossible to escape from, because ice reflects sunlight back into space, preventing the planet from warming up. But eventually volcanic activity continued to release carbon dioxide into the atmosphere, and because there was no liquid water and no active weathering to remove it, the greenhouse gases gradually built up until they reached concentrations high enough to begin melting the ice. But once the melting started, it probably happened relatively quickly in geological terms, perhaps only a few thousand years, as the exposure of dark rock and water allowed the planet to absorb more sunlight and warm up even faster. The end of a Snowball Earth period would have been a time of dramatic climate change, with the planet swinging from frozen to hot, with intense weathering and erosion as rain fell on the newly exposed land, with changes in ocean chemistry that would have had profound effects on any life that had survived the freeze. And somehow, life did survive, preserved in whatever refuges existed during the frozen period, ready to expand and diversify once conditions improved. In the aftermath of the Snowball Earth events, something remarkable happened in the oceans. The simple microscopic life that had dominated for billions of years suddenly began to evolve into more complex forms, larger organisms with differentiated cells, with specialized tissues and organs, with bodies that could be seen with the naked eye. This explosion of evolutionary innovation is called the Ediacaran period, named after the Ediacara Hills in Australia, where fossils from this time were first discovered. Strange and beautiful impressions in ancient rocks showing organisms unlike anything alive today. These Ediacaran organisms were soft-bodied creatures, lacking the hard shells and skeletons that would evolve later, and for a long time scientists debated whether they were even animals at all, or perhaps represented a completely different experiment in multicellular life that left no descendants. Today, most researchers believe that at least some of the Ediacaran organisms were indeed early animals, perhaps related to modern groups like jellyfish and worms, though others remain mysterious and difficult to classify. The Ediacaran world was a strange place by modern standards, with animals that looked like fronds and discs and quilted mattresses lying on the sea floor, filter feeding or perhaps photosynthesizing with the help of symbiotic algae, living in shallow seas where sunlight could penetrate. There were no predators yet, no animals hunting and eating other animals, and so these early complex organisms could live peacefully on the seafloor without fear, slowly extracting nutrients from the water or the sediment around them. The ocean chemistry during the Ediacaran period was different from today, with lower oxygen levels and different concentrations of various minerals, and this may have favoured these soft-bodied, often flat organisms that could absorb oxygen and nutrients across their body surfaces. The continents were still scattered after the breakup of Rodinia, and life remained confined to the oceans, with the land still barren and lifeless, though some microbes may have formed thin crusts on moist rocks near water sources. The first tiny pioneers preparing the way for the invasion of the land that would come much later. The Ediacaran period came to an end around 540 million years ago with the beginning of the Cambrian period, and with it came one of the most dramatic events in the history of life, the Cambrian explosion. This was a time when animal life suddenly diversified to an extraordinary degree, with most of the major groups of animals that exist today appearing in the fossil record within a relatively short span of time, perhaps just 10 or 20 million years. Suddenly, there were animals with hard shells and external skeletons, animals with eyes and teeth and grasping appendages, animals that could swim and burrow and crawl across the seafloor with purpose and speed. The first predators appeared, animals that hunted other animals for food, and this set off an evolutionary arms race as prey species evolved defences and predators evolved ways to overcome those defences. The Cambrian seas were a riot of strange and wonderful forms, trilobites with their segmented bodies and compound eyes, and anomalocaridids that were the top predators of their time with grasping appendages and circular mouths. Strange creatures like hallucigenia with spines along its back and tentacles along its belly, so odd that when scientists first reconstructed it, they could not even tell which end was the head. While life was undergoing its spectacular diversification during the Cambrian explosion, the continents were once again on the move, beginning another cycle of assembly that would lead to the formation of a new supercontinent.
The fragments of Rodinia had drifted apart and were now beginning to come back together,
though in a completely different arrangement from before, because the journey each continent takes is unique, determined by the pattern of convection currents in the mantle below, by the locations of subduction zones where oceanic crust sinks back into the Earth's interior, by the accidents of geography that determine which continents collide with which. Around 600 million years ago, several large continents began to converge in the southern hemisphere, including what would eventually become South America, Africa, Antarctica, Australia, India, and Arabia, coming together to form a massive landmass that geologists call Gondwana, a name derived from a region in India where rocks from this ancient continent are particularly well exposed. Gondwana was not yet a complete supercontinent because other continents remained separate, scattered around the globe in the northern hemisphere, but it was nevertheless enormous, one of the largest land masses in Earth's history, stretching from the South Pole well into the northern hemisphere at its greatest extent. The assembly of Gondwana took place over hundreds of millions of years, with different pieces joining at different times, and the collision of these continents pushed up enormous mountain ranges, including some that would later erode away completely, and others that still exist today as ancient worn-down chains like the Appalachians and the mountains of Scotland and Scandinavia, which were all once connected as part of a much larger range that formed when different parts of Gondwana collided. The climate of Gondwana varied tremendously because of its enormous size, with ice caps at the South Pole, temperate zones in the middle latitudes, and tropical regions near the equator, creating a range of environments from frozen wasteland to steaming jungle. Life during the time of Gondwana continued to evolve and diversify at a rapid pace, with plants finally colonizing the land during the Ordovician and Silurian periods, starting as small, simple things not much different from mosses, but gradually evolving into larger and more complex forms, ferns, and then trees with woody stems that could grow tall and support their weight against gravity. The colonization of the land by plants had profound effects on the Earth's climate and geology, because plant roots break up rock and accelerate weathering, removing CO2 from the atmosphere and potentially cooling the climate, while dead plant material accumulates in swamps and eventually turns into coal, locking away carbon for millions of years. Animals followed plants onto the land, first as small arthropods like millipedes and primitive insects, then as amphibians that still needed to return to the water to reproduce, and finally as reptiles with waterproof eggs that could live their entire lives on dry land. By the time Gondwana was fully formed, the land was no longer barren but was covered with forests and inhabited by an increasing variety of animals, though these were forests and animals very different from what we see today. Gondwana, massive as it was, represented only part of the world's landmass, and the other continents, scattered in the northern hemisphere, were also moving, carried by the tectonic plates across the surface of the Earth, gradually converging toward Gondwana. Around 300 million years ago, these northern continents began to collide with Gondwana, welding themselves to its northern edge and creating a single, unified landmass that contained virtually all of the Earth's continental crust. This ultimate supercontinent is the one we call Pangea, from Greek words meaning all Earth. And it was the last true supercontinent, the most recent time in Earth's history, when all the continents were joined together. Pangea was surrounded by a single vast ocean called Panthalassa, and had a large embayment or gulf on its eastern side called the Tethys Sea, which separated different parts of the supercontinent and provided important marine habitats. The formation of Pangea was marked by mountain building on an epic scale, as the collision of the northern continents with Gondwana pushed up the Appalachian Mountains in North America and the mountains of Europe and Asia. Ranges that were once as tall as the Himalayas are today, that have since been worn down by hundreds of millions of years of erosion. The climate of Pangea was extreme, with vast deserts in the interior of the supercontinent where almost no rain fell because the centre of the landmass was so far from any ocean that moisture could not reach it, while the coasts experienced more moderate conditions with seasonal rainfall. The formation of Pangea also coincided with dramatic changes in life on Earth, including the worst mass extinction in the planet's history at the end of the Permian period, around 250 million years ago, when more than 90% of all species in the oceans and 70% of species on land went extinct, possibly due to massive volcanic eruptions in what is now Siberia that released enormous amounts of greenhouse gases and poisoned the oceans and atmosphere. Life recovered from this catastrophe, as it always has, and the Triassic period that followed saw the rise of new groups of animals, including the dinosaurs, which would dominate terrestrial ecosystems for the next 150 million years. The early dinosaurs were small, agile creatures, but they would eventually evolve into the largest land animals that have ever lived, as well as an enormous variety of other forms adapted to every possible way of life, from tiny insect eaters to massive herbivores to fearsome predators. Mammals also appeared during the Triassic, but they remained small and mostly nocturnal, living in the shadow of the dinosaurs, waiting for their opportunity to diversify and dominate, which would not come until after the dinosaurs went extinct at the end of the Cretaceous period. Pangea began to break apart during the Jurassic period, around 200 million years ago, with rifts opening first between what would become North America and Africa, creating the early Atlantic Ocean, then later separating other continents, eventually leading to the configuration of land masses we see today. Now we must ask a question that might seem absurd at first, a question that pushes against the boundaries of everything we think we know about the history of life on Earth. If supercontinents have formed and broken apart multiple times throughout Earth's history, if Pangea was only the most recent in a long line of such land masses stretching back billions of years, is it possible that something we might call a civilization existed on one of these older supercontinents? The very idea seems to contradict everything science tells us, because we know from the fossil record that complex life only evolved relatively recently in Earth's history. that humans appeared only a few 100,000 years ago, a mere eye blink compared to the billions of years that the Earth has existed. We know that the land was lifeless for most of Earth's history, that plants and animals only colonized the continents in the last 500 million years or so, that anything we would recognize as intelligent life evolved far more recently still. But let us think more carefully about what we mean by civilization and what evidence such a thing might leave behind. A civilization, at its most basic, is an organized society with specialized roles, with the ability to manipulate its environment in significant ways, with some form of communication and cultural transmission from one generation to the next. By this definition, humans are not the only civilization on Earth today. We might argue that some social insects like ants and termites, with their complex societies and sophisticated nest-building behaviors, meet at least some of these criteria. Could something analogous have existed in the deep past during one of the earlier supercontinents, long before humans or even mammals evolved? The immediate scientific answer would be no, because we have no evidence for any kind of complex life forms, let alone intelligent ones, existing before the Ediacaran period at the very earliest, and even the Ediacaran organisms appear to have been simple, passive filter feeders without anything resembling intelligence. Yet we must acknowledge how fragmentary our knowledge of the deep past really is. The fossil record becomes increasingly sparse and difficult to interpret as we go further back in time, because older rocks are more likely to have been destroyed by erosion, buried deep beneath younger rocks, or transformed by heat and pressure into metamorphic rocks where any fossils they once contained had been obliterated. Soft-bodied organisms leave fossils only under exceptional circumstances, and even hard-shelled creatures are rarely preserved. For every organism that becomes a fossil, millions or billions live and die without leaving any trace. Could there have been complex soft-bodied organisms living on land during some earlier period? Organisms that left no fossils because their environment was not conducive to preservation? Could there have been something analogous to intelligence, some form of organized behavior, some manipulation of the environment that left traces so subtle or so degraded by time that we have not recognized them? A few years ago, two scientists named Gavin Schmidt and Adam Frank published a thought experiment they called the Silurian hypothesis, named after a race of intelligent reptiles from a science fiction television show. They asked what traces an industrial civilization might leave in the geological record if it existed millions of years in the past and then disappeared. Their conclusion was sobering. Even a civilization that lasted for hundreds of thousands of years, that built cities and roads and factories, that altered the chemistry of the atmosphere, might leave traces that would be almost impossible to detect after more than a few million years, and certainly after hundreds of millions of years. Buildings would erode away, metals would corrode and be dispersed, plastics would break down, even changes to atmospheric chemistry would be smoothed out by natural processes. What might remain would be subtle signals, anomalies in the isotope ratios of certain elements perhaps, or unusual concentrations of rare metals, or changes in the types of fossils that appear in the geological record. The point of the Silurian hypothesis is not to suggest that such an ancient civilization actually existed. The scientists who proposed it are clear that there is no evidence for any such thing, but rather to make us think about what kind of evidence we should be looking for, and to highlight how difficult it would be to detect. If a civilization existed on Earth just 50 million years ago during the early Eocene period, when the planet was much warmer than it is today and forests grew almost to the poles, it is quite possible that we would have found no trace of it by now, or that we have found traces but not recognized them for what they are. The further back in time we go, the less likely we are to find any evidence at all, because more time means more opportunity for erosion, for transformation of rocks, for any signals to be buried or destroyed. If we consider the possibility of something existing on Rodinia more than 1 billion years ago, or on one of the even earlier supercontinents, the challenges become almost insurmountable, because rocks from those times are rare and often highly metamorphosed, their original character transformed by heat and pressure deep within the Earth. But perhaps we are thinking about this in the wrong way, looking for the wrong kind of evidence. Human civilization, and any civilization we could imagine that resembles it, requires large-brained, intelligent creatures capable of complex thought and planning, and such creatures require a long evolutionary history, millions of years of evolution from simpler ancestors. We can trace human evolution back through various species of early humans and apes, back to primitive primates, back to small mammals, back to reptile-like ancestors, back and back through the entire history of complex life on Earth. Every stage of this evolution is supported by fossil evidence, incomplete as that evidence may be, and we can see that the capabilities required for civilization, large brains, complex social behavior, sophisticated tool use, only evolved relatively recently. Even the most intelligent animals alive before humans, the various extinct species of humans and human relatives, left only crude stone tools and showed no signs of anything we would call civilization. Perhaps, though, we are being too narrow in our thinking, too constrained by our human-centered view of what intelligence and civilization must look like. Life on Earth for most of its history has been dominated by microbes, single-celled organisms like bacteria and archaea and later eukaryotes. And while we do not usually think of these organisms as intelligent, they are capable of remarkably sophisticated behaviors. Bacteria can sense their environment and respond to it, moving toward food sources and away from harmful chemicals, communicating with each other through chemical signals, coordinating their behavior in ways that benefit the group even at cost to individuals. Some bacteria form elaborate structures called biofilms, complex communities of many different species living together in a matrix of sticky substances they secrete, dividing up resources and occupying different ecological niches within the tiny world of the biofilm. Bacterial colonies can even exhibit something like memory, changing their behavior based on past experiences, though this is memory stored in chemical states rather than in neural connections. Could something like a microbial civilization have existed on one of the ancient supercontinents, a planetary-scale community of microbes living in the soil and shallow waters, exchanging signals, coordinating their metabolisms, perhaps even collectively manipulating their environment in ways that increased their survival and reproduction? This is of course pure speculation, but it is perhaps not entirely impossible. We know that microbes can have enormous effects on their environment. The photosynthetic bacteria that produced oxygen during the Great Oxidation Event transformed the entire atmosphere of the planet, an achievement that no single species civilization of macroscopic organisms has ever matched. We know that biofilms can be remarkably complex, with different species occupying different roles, with structures that in some ways resemble the organs of multicellular organisms. Could such a system, spread across an entire continent, evolved over hundreds of millions of years, have developed capabilities we would not expect from simple bacteria? The evidence for such a thing would be subtle indeed, perhaps nothing more than unusual chemical signatures in ancient rocks, or patterns in the distribution of minerals that suggest biological processing, or isotope ratios that hint at metabolic activity. Some researchers have proposed that certain unusual geological formations from the distant past, such as banded iron formations or particular types of stromatolites, might reflect not just the presence of microbes, but their organized, coordinated activity on large scales. These ideas remain controversial and speculative, but they remind us that absence of evidence is not evidence of absence, and that the history of life on Earth may contain chapters we have not yet imagined, let alone discovered. The challenge is to think of ways to test these ideas, to identify what specific evidence we should look for, and to distinguish signals of organized biological activity from the results of purely geological or chemical processes. our search for possible ancient civilizations or organized life forms on pre-Pangean supercontinents must also consider the possibility of life existing in places we cannot easily observe, hidden away from the surface world where erosion and geological processes have destroyed most traces of the past. In recent decades, scientists have discovered that life exists not just on the surface of the Earth and in the oceans, but deep within the solid rock of the continents and the ocean floor, sometimes kilometers below the surface. This deep biosphere, as it is called, consists mainly of bacteria and archaea that live in tiny pores and cracks in the rock, making their living from chemical reactions between the rock and groundwater, completely independent of sunlight and of the food chains that depend on photosynthesis. These deep-dwelling microbes grow extremely slowly and can survive for thousands or even millions of years in a kind of suspended animation, waiting for conditions to improve, and they may represent a significant fraction of all the biomass on Earth. The existence of this deep biosphere raises intriguing questions about the history of life on our planet. If microbes can live deep within solid rock, then they would be protected from surface catastrophes like asteroid impacts and volcanic eruptions and even the snowball Earth events that froze the surface. They would also be protected from erosion and from most of the geological processes that destroy fossils, meaning that traces of ancient deep biosphere communities might be preserved in rocks that are billions of years old, if only we knew how to recognize them. Could the deep biosphere of the ancient supercontinents have been more extensive and more complex than what we see today? Could there have been vertical connections between surface communities and deep communities, with materials and energy flowing between them, creating ecosystems that extended from the sunlit surface down to the lightless depths where only chemosynthesis is possible? Some researchers have speculated that the deep biosphere might have been especially important during the long periods when the Earth's surface was hostile to life, such as during snowball Earth events or during the heavy bombardment period early in Earth's history when asteroids and comets were still frequently striking the planet. During these times, the deep rocks might have been the only safe haven for life, a refuge from which the surface could be recolonized once conditions improved. If this is true, then the continuity of life on Earth might have been maintained by deep-dwelling microbes that left little or no trace in the surface rocks we can study, making the history of life even more hidden and fragmentary than we already know it to be. The search for evidence of ancient deep biosphere communities is extremely challenging, requiring sophisticated chemical and isotopic analyses of ancient rocks, looking for subtle signals that might indicate biological activity as opposed to purely geological processes. Another place where evidence of ancient organized life might hide is within the crystals and minerals that make up rocks, particularly very ancient rocks that have survived from the earliest days of Earth's history. Crystals grow by adding layers of atoms in a regular, repeating pattern, and as they grow they can trap tiny inclusions of fluid or other materials that were present in the environment at the time of formation. These inclusions act like time capsules, preserving samples of ancient water or air or organic material that can be analysed billions of years later to reveal information about conditions on the early Earth. Scientists have found organic molecules in crystals of quartz and zircon that are more than 3 billion years old, providing direct chemical evidence of life at that time, even though no fossils of the organisms themselves have been preserved. Could more complex information be preserved in such crystals? Some researchers have proposed that the arrangement of defects and impurities within crystals might, under certain circumstances, preserve patterns that reflect biological activity, almost like a mineral memory of past life. This idea is highly speculative and controversial, but it is based on the fact that biological systems often create highly ordered structures and that the formation of minerals in the presence of organisms can be influenced by their metabolic activity, potentially creating patterns that would not occur in purely inorganic processes. If ancient microbes or even more complex organisms were living on the surface of one of the pre-Pangean supercontinents, Their activity might have influenced the formation of minerals in ways that could still be detected today if we knew what to look for and had sensitive enough techniques to detect such subtle signals. Study of ancient crystals has already revealed surprises about the early Earth, including evidence that liquid water was present on the surface much earlier than scientists previously thought, based on oxygen isotope ratios in zircon crystals that are more than 4 billion years old. These tiny crystals, some smaller than a grain of sand, are among the oldest materials on Earth, having survived multiple cycles of erosion, burial, heating and mountain building that destroyed the rocks they originally formed in. Inside these durable mineral time capsules might be chemical clues to the history of early life, clues that could potentially reveal whether life was more complex or more widespread in the distant past than the fossil record suggests. The techniques for analyzing these crystals continue to improve, allowing scientists to detect smaller and smaller amounts of organic material and to characterize its chemical structure in increasing detail, opening new windows into the deep past. As we contemplate the possibility of ancient civilizations or organized life on pre-Pangean supercontinents, we must confront one of the most fundamental challenges facing anyone who tries to understand Earth's history: the problem of deep time. The Earth is 4.5 billion years old, a span of time so vast that the human mind simply cannot grasp it through intuition or everyday experience. 1 million years is a long time, long enough for species to evolve and go extinct, for mountains to rise and erode away, for rivers to carve new courses across continents. But 1 million years is only 1,000th of a billion years, and the Earth has existed for 4,500 times even that vast span. The oldest supercontinent we have discussed, Rodinia, existed 1 billion years ago, which means it is separated from us by a span of time twice as long as the entire time that complex life has existed on Earth. When we think about such vast periods of time, we must remember that erosion and geological processes are constantly destroying the record of the past. Rocks exposed at the surface are broken down by weathering, with their particles carried away by wind and water to be deposited elsewhere as sediment. Mountains that once towered kilometers into the sky are worn down to low hills and eventually to plains, with their rocks recycled into new formations. Old ocean floors are pulled down into the mantle at subduction zones, melted and destroyed, with no trace remaining of whatever might have existed on them. The crust of the continents is constantly being reworked, with old rocks melted and recrystallized or buried so deep that heat and pressure transform them beyond recognition. The result is that rocks older than a few 100 million years are relatively rare, and rocks older than 1 billion years are very rare indeed, often found only in a few ancient cores of the continents called cratons, where they have somehow escaped destruction. Even when ancient rocks survive, the information they contain degrades over time. Fossils are destroyed by the pressure of overlying rocks or by chemical changes that replace original material with minerals. The textures and structures that tell geologists about how a rock formed become obscured by later changes. Chemical signatures that might indicate biological activity become mixed and contaminated by later fluids moving through the rock. Searching for evidence of ancient life or civilization in rocks billions of years old is like trying to read a book that has been left out in the rain for years, with most of the pages missing and the remaining ones faded and water-stained almost to illegibility. We can make out a few words here and there, perhaps a sentence or two, but the overall story is lost, and we can only guess at what the complete text might have said. This is why claims about the deep past must always be tentative and qualified, supported by multiple lines of evidence and subject to revision as new information becomes available. In our search for evidence of ancient civilizations or organized life on pre-Pangean supercontinents, we have so far assumed that any such life would be based on the same chemistry as modern life, using DNA to store genetic information, using proteins as structural materials and enzymes, using lipids to form cell membranes. This is a reasonable assumption, because all life on Earth today shares these fundamental biochemical features, suggesting that we all descend from a common ancestor that already possessed them. But we must also consider the possibility that alternative forms of life might have existed in the past, using different chemical systems, perhaps existing alongside the ancestors of modern life, or perhaps flourishing at times and places where conditions were unsuitable for DNA-based life as we know it. Scientists studying the origin of life have proposed various scenarios in which the first living systems might have been based on different molecules than those used by modern cells. Perhaps the earliest life used RNA instead of DNA to store genetic information, RNA being a simpler molecule that can both store information and catalyze chemical reactions, potentially allowing it to fulfill both of the key functions needed for life. Perhaps early cells used different types of molecules for their membranes, or different chemical reactions for their metabolism, and the modern biochemistry we see in all living things only became established later, after these alternative systems were outcompeted and went extinct. Such alternative life forms did exist. They might have left chemical traces in ancient rocks that we would not recognize as biological, because they do not match the patterns we associate with modern life. An even more exotic possibility is that life might have existed based on entirely different chemical principles. Not carbon-based life that uses water as a solvent, but perhaps silicon-based life, or life using other liquids like ammonia or methane. These ideas, long popular in science fiction, have been studied seriously by some astrobiologists, thinking about what forms life might take on other planets with very different conditions from Earth. While most scientists believe that carbon and water are uniquely suited for the complex chemistry needed for life, because of carbon's ability to form many different types of bonds and water's excellent properties as a solvent and medium for chemical reactions, we cannot completely rule out the possibility that alternative chemistries might work under certain conditions. If such exotic life ever existed on Earth, it would most likely have been in the very early days of the planet, when conditions were different from anything we see today, or perhaps in isolated environments where unusual chemistry created temporary opportunities. As we think about the possibility of ancient civilizations or organized life, we should consider a hypothesis that suggests the Earth itself as a whole might exhibit characteristics of a living system. The Gaia hypothesis, proposed by scientist James Lovelock and microbiologist Lynn Margulis in the 1970s, suggests that life on Earth does not merely adapt to its environment, but actively modifies that environment to keep conditions suitable for life. According to this view, the atmosphere, the oceans, the temperature of the planet, and the chemistry of rocks and soil are all influenced by living organisms in ways that create a kind of planetary scale homeostasis, keeping conditions stable even as external factors like the sun's brightness change over time. The name Gaia comes from the ancient Greek goddess of the earth, reflecting the idea of the planet as a kind of superorganism. The Gaia hypothesis has been controversial in science, with some researchers embracing it as a useful framework for thinking about how life and environment interact, while others criticize it as being too vague or as attributing purpose and intentionality to natural processes that are really just the automatic result of evolution by natural selection. Nevertheless, there is good evidence that life has had profound effects on the Earth's environment over geological time. The oxygen in our atmosphere is there because of photosynthetic organisms, and would disappear within a few million years if photosynthesis stopped. The temperature of the Earth has remained within a range suitable for liquid water for billions of years, despite the fact that the sun has gotten brighter over that time, possibly because weathering rates and atmospheric carbon dioxide levels have been regulated by biological processes. The chemistry of the oceans is influenced by the activity of countless microbes that cycle elements like nitrogen, sulfur, and iron through different chemical forms. If we take the Gaia hypothesis seriously, then perhaps what we should be looking for is not evidence of a civilization in the sense of a single intelligent species, but rather evidence of planetary scale self-organization, of life collectively modifying its environment in coordinated ways that increase the overall habitability of the planet. The Great Oxidation Event might be seen as an example of this, a moment when life transformed the entire atmosphere of the planet, creating new opportunities for more complex organisms to evolve, while also causing the extinction of many species that could not adapt to the change. Could there have been other such events in Earth's history, moments when life reorganized itself and its environment in fundamental ways, leaving chemical or geological signatures that we have not yet recognized as significant? The challenge is to distinguish true coordination and organization from the appearance of such things created by purely random or evolutionary processes acting independently. Throughout the world, in rocks of various ages, geologists have discovered formations and structures that remain difficult to explain fully, anomalies that do not fit easily into our understanding of how rocks and landscapes normally form. Some of these anomalies have been eventually explained through improved understanding of geological processes, while others remain mysterious, their origins debated by experts with different interpretations. Could any of these unexplained formations be evidence of ancient organized life, or even something approaching a civilization? The short answer from mainstream geology is no. All known formations can be explained, at least in principle, by natural geological and biological processes without invoking anything as exotic as an ancient civilization. But it is worth considering some of these anomalies and thinking about what kind of evidence might actually be convincing if it were found. One category of geological anomalies involves highly ordered or geometric structures found in rocks. Certain types of minerals naturally form crystals with regular geometric shapes, and some rocks show patterns of layering or jointing that can create remarkably regular structures, sometimes resembling walls or roads or building blocks. The famous Giant's Causeway in Northern Ireland, with its thousands of hexagonal basalt columns fitting together like a honeycomb, is a natural formation created by the cooling and contraction of lava. But to ancient people who did not understand this geological process, it seemed so regular and purposeful that they attributed it to giants or heroes of legend. Many supposed ancient structures that appear in fringe theories about lost civilizations turn out to be natural geological formations that happen to have regular shapes, and geologists have become adept at recognizing the characteristics that distinguish natural from artificial structures. Another category involves unusual concentrations of certain elements or minerals in particular locations. Most geological processes distribute materials in patterns that follow physical and chemical laws, with concentrations reflecting factors like the solubility of minerals, the density of materials, and the flow of water or magma. But biological processes can also concentrate materials, sometimes in ways that seem unusual or unexpected from a purely geological perspective. For instance, the banded iron formations we mentioned earlier show alternating layers of iron-rich and iron-poor rock that reflect the seasonal or cyclical activity of photosynthetic bacteria billions of years ago, a pattern that would be difficult to explain without invoking biology. If ancient organized life or microbial civilizations existed, they might have left behind unusual patterns of mineral concentration or depletion, or might have created structures that are difficult to explain by normal geological processes. Though distinguishing such evidence from the results of unusual but purely natural processes would be extremely challenging. When most people think about ancient civilizations, they imagine technology, tools and machines and structures that demonstrate the ability to manipulate materials and energy in sophisticated ways. Human civilization is intimately tied to our technology, from the simple stone tools of our earliest ancestors to the computers and spacecraft of the modern world. We naturally tend to think that any civilization worthy of the name would leave behind technological artifacts. But as we have already discussed, even sophisticated technology might leave almost no trace in the geological record after millions of years, let alone hundreds of millions or billions. Metals corrode and oxidize, eventually dispersing into the environment as scattered atoms mixed with natural ores. Stone structures are broken down by erosion and weathering, reduced to gravel and sand, and eventually to clay minerals that retain no memory of their original form. Even materials that seem incredibly durable, like plastics or ceramics, will eventually break down under the assault of geological time. Some researchers have proposed that we might find evidence of ancient technology in the form of synthetic materials or compounds that do not occur naturally, such as particular types of plastics or alloys or refined elements. The problem with this approach is that we need to be absolutely certain that the material in question could not be produced by any natural process, and this is harder to prove than it might seem, because nature is creative and sometimes produces results that seem artificial. For instance, native metals like copper and gold are sometimes found in surprisingly pure form in natural deposits, and nuclear reactions occurring naturally in uranium ore bodies have produced traces of elements that we normally associate only with artificial nuclear reactors. Any claim that a particular material is artificial and must have been produced by some ancient civilization would need to withstand intense scrutiny and exclude all possible natural explanations, a high bar to meet given how complex and varied geological processes can be. Another approach to searching for ancient technology would be to look for changes in the environment that could only have been caused by industrial activity, such as widespread pollution with heavy metals or changes in the ratios of carbon isotopes that might indicate the burning of fossil fuels. This is essentially what the Silurian hypothesis explores, asking what geochemical signatures an industrial civilization would leave behind. The challenge is that many of the signatures we might look for, such as elevated levels of carbon dioxide in the atmosphere or increased erosion due to deforestation, can also be caused by natural events like volcanic eruptions or climate changes that have nothing to do with civilization. To be convincing, any such signature would need to show patterns that clearly indicate a biological and specifically a technological origin, such as isotope ratios that could only come from industrial processes, or concentrations of synthetic materials in sediments of a particular age. So far, no such evidence has been found in rocks older than the most recent few tens of millions of years. And even the signals we see from that period are entirely consistent with natural processes without invoking any extinct civilizations. The history of complex life on Earth has been punctuated by mass extinctions, periods when a large fraction of all species died out within a relatively short time. The 5 major mass extinctions are well known: the end Ordovician, the late Devonian, the end Permian, the end Triassic, and the end Cretaceous that killed the dinosaurs. But there have been many smaller extinction events as well, and some researchers argue that mass extinctions are actually a regular occurrence, happening with a certain frequency throughout Earth's history. These extinctions have many causes: asteroid impacts, massive volcanic eruptions, climate change, changes in ocean chemistry, and sometimes combinations of multiple factors happening at once. Each mass extinction represents a catastrophe for the species that go extinct, but also an opportunity for other species to diversify and evolve into ecological niches that were previously occupied, resetting the evolutionary game board and allowing new forms of life to flourish. If an ancient civilization or organized life form existed on one of the pre-Pangean supercontinents, it might have been wiped out by a mass extinction, leaving only fragmentary traces that we have not yet recognized. This is one possible explanation for why we find no clear evidence of such things. If they were destroyed completely or nearly so by some catastrophe, and if only a few scattered fossils or chemical traces survived, we might easily miss them or misinterpret them as something else. The mass extinction at the end of the Permian, the worst in Earth's history, killed more than 90% of all species in the oceans and 70% on land, and came very close to ending complex life entirely. If something similar happened even earlier in Earth's history, before the evolution of complex life as we know it, it might have wiped out whatever unusual or organized life forms had evolved up to that point, forcing evolution to start over from simpler forms. The causes of mass extinctions also raise interesting questions about the stability of life on Earth and whether certain types of organisms or civilizations might be especially vulnerable. If a civilization developed technology that altered the environment in significant ways, it might make itself more vulnerable to certain types of catastrophes, or it might inadvertently trigger environmental changes that led to its own extinction. Human civilization is currently changing the Earth's climate and causing a rapid loss of biodiversity that some scientists already classify as the beginning of a sixth mass extinction, demonstrating that intelligence and technology do not necessarily protect a species from existential threats and can in fact create new ones. If an ancient civilization existed and then went extinct, understanding what caused its demise might offer valuable lessons for our own future, though of course this is highly speculative since we have no evidence that such a civilization ever existed. The question of ancient civilizations on Earth connects in interesting ways to a larger question about life and intelligence in the universe, the Fermi paradox. This paradox, named after physicist Enrico Fermi, asks why, if the universe is so vast and contains so many stars and planets, we have not yet detected any signs of extraterrestrial civilizations. There are billions of galaxies, each containing billions of stars, and we now know that planets are common around those stars, so it seems like there should be many opportunities for life to evolve and eventually develop intelligence and technology. Yet despite decades of searching, we have found no convincing evidence of extraterrestrial intelligence, no radio signals that clearly come from alien civilizations, no signs of massive engineering projects or other activities that an advanced civilization might undertake. This absence of evidence has led to much speculation about why we seem to be alone, or at least why we have not yet made contact with anyone else. One possible explanation for the Fermi paradox is that civilizations, once they arise, do not last very long on cosmic timescales, perhaps because they destroy themselves through war or environmental damage, or because they face some inevitable catastrophe that wipes them out before they can expand beyond their home planet. If this is true, then the universe might be full of the ruins of dead civilizations, scattered across planets around countless stars, but we would not detect them because they are extinct and have left only subtle traces that we cannot see from light years away. If ancient civilizations existed on Earth itself and then went extinct, leaving little or no trace behind, this would be consistent with the idea that civilizations are common but short-lived, appearing and disappearing like sparks in the night, never lasting long enough to make their presence known across interstellar distances. Another possible explanation for the Fermi paradox is that intelligence and civilization are actually much rarer than we think, that some step in the process from simple chemicals to spacefaring civilization is so difficult or unlikely that it almost never happens. Perhaps the origin of life itself is the difficult step, or perhaps the evolution of complex multicellular organisms, or perhaps the evolution of intelligence, or perhaps the development of technology. If we knew that a civilization had existed on Earth in the deep past, before humans, this would tell us that at least on our planet, the evolution of civilization is not a one-time fluke but something that can happen more than once given enough time, which would suggest that it might be more common in the universe than we think. Conversely, if we are convinced that no such ancient civilization existed, then Earth's history teaches us that intelligence and civilization require very specific conditions and a very long evolutionary preparation, making it potentially quite rare even in a universe as large as ours. Some researchers searching for evidence of ancient organized life or intelligence have looked for mathematical patterns in geological formations or in the fossil record, arguing that certain types of patterns would be unlikely to arise from purely natural processes and might indicate purposeful design or organization. One pattern that has attracted particular attention is the golden ratio, approximately 1.618, a number that appears frequently in nature, in the spiral of nautilus shells, the arrangement of seeds in a sunflower, the proportions of the human body, and many other places. The golden ratio has been celebrated since ancient times for its aesthetic and mathematical properties, and some people believe it represents a fundamental principle of nature, or even of consciousness itself. The appearance of the golden ratio and related mathematical patterns in nature is well documented, but there is significant debate about what it means. Some scientists argue that these patterns arise naturally from the physics and mathematics of growth processes, from the way cells divide and structures develop, following simple rules that inevitably produce certain proportions. According to this view, the golden ratio is simply a consequence of optimization. Things tend to grow in ways that efficiently pack space or distribute resources, and these efficient arrangements often involve proportions related to the golden ratio. There is no need to invoke consciousness or design, just mathematics and physics playing out in the developing organism or structure. Other researchers, particularly in fields on the fringe of mainstream science, argue that the widespread appearance of these patterns suggests something deeper, perhaps a kind of mathematical intelligence inherent in nature itself, or perhaps evidence that ancient advanced beings understood these principles and built them into the fabric of reality somehow. When applied to the search for ancient civilizations, the argument about mathematical patterns becomes even more speculative. Some claim to find the golden ratio or other special numbers in the dimensions or alignments of certain geological formations or in patterns in the fossil record, and they argue that these patterns are too precise or too widespread to be coincidental, that they must indicate intelligent design. The problem with these arguments is that humans are very good at finding patterns, even in random data, a tendency called pareidolia, and we often see significance in patterns that actually have no special meaning. When looking at complex data like geological formations or fossil distributions, it is almost always possible to find some numerical relationships or patterns if you look hard enough and are willing to be selective about what data you include. But this does not mean the patterns are real or meaningful. Any claim that mathematical patterns provide evidence of ancient intelligence needs to demonstrate that the patterns could not have arisen by chance or through known natural processes, a very difficult standard to meet. Pushing our speculation even further, some philosophers and scientists have proposed that consciousness might not be a property that only emerges in complex brains, but might instead be a fundamental feature of the universe itself, present to some degree in all matter. This idea, called panpsychism, has a long history in philosophy and has been taken up by some modern thinkers trying to solve the hard problem of consciousness, the question of how and why subjective experience arises from physical processes in the brain. According to panpsychism, even simple particles like electrons might have some extremely basic form of consciousness or experience, and the consciousness we experience as humans is the result of countless tiny consciousnesses combining and organizing themselves into a complex system. This is a controversial idea that most scientists do not accept, but it raises interesting questions about what we mean by consciousness and whether it might exist in forms very different from what we experience. If some form of consciousness or awareness is indeed a fundamental property of matter, then perhaps the organization of matter into living systems and the further organization of those systems into complex societies and ecosystems represents a kind of ongoing experiment in conscious complexity that has been happening since the beginning of the universe. By this view, even the earliest life on Earth, simple microbes in the ancient oceans, were participating in the universe's exploration of consciousness and organization. The formation of supercontinents, the evolution of increasingly complex life forms, the eventual appearance of intelligent species like humans, all of these would be part of a larger pattern of increasing complexity and organization that might be seen as the universe becoming more conscious or aware of itself. Ancient civilizations, if they existed, would represent earlier experiments in this process, attempts by the universe to organize matter in conscious, purposeful ways. This kind of speculation is far beyond what can be tested by science in any direct way, moving into the realm of philosophy and metaphysics. But it offers a different framework for thinking about the questions we have been exploring. Instead of asking whether a civilization in the conventional sense existed on pre-Pangean supercontinents, we might ask whether there were organized systems of any kind that exhibited properties like awareness, purposefulness, and collective behavior, even if those systems were not made of individual organisms with brains. We might look for evidence of increasing complexity and organization over time, of patterns that suggest life was not just randomly drifting through evolution, but was in some sense exploring possibilities, learning from past experiments, building towards something. The geological record does show a general trend toward increasing complexity over time, from simple microbes to multicellular organisms to ecosystems with intricate food webs and relationships, though this trend is not smooth or inevitable and has been interrupted many times by extinctions and setbacks. Throughout human history, cultures around the world have told stories about ancient times when the world was different, when great civilizations rose and fell, when gods or heroes walked the earth, when cataclysms reshaped the land and destroyed entire peoples. These myths and legends are fascinating from a cultural and psychological perspective, revealing how different societies think about time, change, and the relationship between humans and nature. But could any of these stories contain actual memories of ancient events? Information about the deep past, transmitted through countless generations by oral tradition before being written down? Some researchers have argued that certain myths might encode real historical events, such as floods caused by rising sea levels at the end of the last ice age, and that careful analysis of these stories might reveal truths about periods before written history. The idea that myths might preserve memories of truly ancient events, millions or billions of years old, is much more difficult to support because oral tradition is simply not that stable over such long periods. Each time a story is told, it changes slightly, details are added or forgotten, the story is adapted to make sense to a new audience or to serve the purposes of the storyteller. Over hundreds or thousands of years, these changes accumulate, and the story that eventually gets written down might bear little resemblance to whatever events inspired the original version. There is also the problem of interpreting the story's myths, are not straightforward historical accounts, but are filled with symbolic language, supernatural elements, and cultural references that made sense to the original audience, but are obscure to us. When we read about ancient battles between gods, or about lost lands that sank beneath the waves, or about previous creations that were destroyed before the current world was made, are we reading about actual events, or about metaphorical ways of thinking about change and time? Despite these challenges, the study of myths and their possible historical basis remains an active area of research, particularly in cases where the myths can be compared with archaeological or geological evidence from the same region. Some stories of floods and volcanic eruptions have been convincingly linked to specific historical events, showing that oral tradition can preserve real information about the past over timescales of centuries. But extending this to the deep geological past, to supercontinents that existed hundreds of millions or billions of years ago, would require that somehow information was transmitted across all the extinctions and evolutionary changes that separate us from that time, perhaps encoded in some form we do not yet understand, in patterns of behavior, or in the very structure of DNA that all life shares. This seems extremely unlikely from a scientific perspective, but it remains a tantalizing possibility that captures the imagination and drives some researchers to look for connections between myth and deep time. As we near the end of our journey through deep time and speculation, we must acknowledge the fundamental limits on what we can know about the distant past. The further back we look, the less information is available, the more difficult interpretation becomes, and the more we must rely on inference and assumption rather than direct evidence. There will always be questions about Earth's history that we cannot answer with certainty, events that left no trace we can detect, organisms that lived and died without being preserved as fossils, environmental changes that happened too quickly, or affected areas too small to leave a clear signal in the geological record. This is frustrating for scientists who value certainty and evidence, but it is also in some ways liberating, because it reminds us that there is still mystery in the world, still things we do not understand, still room for imagination and speculation even as we pursue rigorous scientific investigation. The question of whether civilizations or organized life existed on pre-Pangean supercontinents is probably one of these ultimately unknowable things, unless we are extremely lucky and somehow find clear, unambiguous evidence that has somehow survived billions of years of geological processes. The absence of such evidence does not prove that nothing unusual existed, because absence of evidence is not the same as evidence of absence, especially when we are talking about events so ancient that most evidence would inevitably have been destroyed. But the absence of evidence does mean that any claims about ancient civilizations must remain speculation. Interesting to think about, but not something we can assert with confidence or build further theories upon. Science advances by making claims that can be tested, by predicting what evidence should exist if a hypothesis is true, and then by looking for that evidence. When evidence cannot exist or cannot be found, science reaches its limits and we enter the realm of philosophy and imagination. Yet the questions themselves remain valuable, even if we cannot answer them definitively, because they push us to think more deeply about what we know and how we know it, about the assumptions we make when interpreting evidence, about the possibility that the history of our planet might be stranger and more complex than the straightforward narrative we usually tell. They also remind us that Earth has a deep and complex history that extends far beyond the brief moment that humans have existed, that our planet has gone through many different phases and will go through many more after we are gone, that the current configuration of continents and climates and ecosystems is just one temporary arrangement in a constantly changing system. This perspective of deep time and constant change can be humbling but also inspiring, connecting us to something larger than ourselves, to the vast sweep of planetary history, and to the possibility that life and consciousness might exist in forms we have not yet imagined. Whether or not ancient civilizations existed on pre-Pangean supercontinents, thinking about these questions has implications for how we understand our own civilization and its place in the larger patterns of Earth history. If civilizations are fragile and temporary, rising for a brief moment only to fall and be forgotten, then this suggests we should not take our own existence for granted, that we face real existential risks that could end human civilization, or even cause human extinction. Climate change, nuclear war, pandemics, asteroid impacts, all of these are threats that could, in the worst case, lead to the collapse of global civilization and the loss of much of what humans have achieved. If this happened, and if humanity somehow survived but was reduced to small, scattered populations without technology or written records, how long would it take before our current civilization was forgotten, reduced to myths and legends, and eventually erased from memory entirely? On the other hand, if complex civilizations are rare and difficult to achieve, if it required the entire 4.5 billion year history of the Earth, with all its accidents and contingencies, to produce even one species capable of understanding the universe and contemplating its own existence, then this suggests we have a responsibility to preserve and extend what we have achieved, because it might be a unique or very rare occurrence not just on Earth, but in the universe as a whole. This is the perspective taken by some philosophers and scientists who argue that humanity's ultimate purpose is to spread life and consciousness beyond Earth, to other planets and eventually to other star systems, ensuring that the light of awareness continues even if something happens to our home planet. Whether you find this perspective inspiring or hubristic depends on your values and beliefs, but it follows logically from the idea that consciousness and civilization might be rare and precious phenomena in a universe that is otherwise mostly lifeless and unconscious. There is also something to be learned from thinking about how future civilizations might view us, If humans go extinct and another intelligent species evolves millions of years from now, or if Earth is visited by alien explorers in the distant future, what traces will we leave behind? Will future geologists be able to detect our presence in the rocks? Or will we have vanished almost without trace, leaving only subtle chemical anomalies and perhaps a few scattered fossils? The study of how long human artifacts and impacts might last in the geological record has led to the proposal of the Anthropocene as a new geological epoch defined by human influence on the planet, with markers like plastics, radionuclides from nuclear testing, and changes in sediment composition due to agriculture and construction. But on the timescales we have been discussing, millions and billions of years, even these markers would become increasingly difficult to detect, worn away by erosion, buried under miles of sediment, or destroyed by plate tectonics. There is something deeply poetic about contemplating the vast stretches of geological time, the slow drift of continents, the rise and fall of mountain ranges, the patient work of erosion carving landscapes over millions of years. It is a perspective that challenges our usual human-centered view of the world, where we think in terms of days and years and perhaps decades, but rarely consider the much longer timescales on which the planet itself operates. The Earth is immensely old, and the current arrangement of its surface features is just one frame in an enormously long movie that has been playing since the planet formed and will continue long after humans are gone. Supercontinents form and break apart in cycles lasting hundreds of millions of years. Oceans open and close, species evolve and go extinct. Yet through all of this, the planet endures, constantly changing but in some sense also remaining the same, following the same basic physical and chemical principles that have governed its behavior since the beginning. When we think about pre-Pangean supercontinents, we are imagining worlds that were as real and solid as the ground beneath our feet today. Places where rain fell and rivers flowed and volcanoes erupted, where the sun rose and set each day just as it does now. Yet these are places we can never visit, times we can never witness, separated from us not just by distance but by the unbridgeable gulf of time. The rocks are our only connection to these ancient worlds, fragmentary and cryptic as they are, and learning to read them is like learning to read a language that is mostly forgotten, where we can make out a few words and phrases but the full meaning often escapes us. Yet even these fragments tell us remarkable things, showing us that the Earth has had a long and complex history, that conditions have changed dramatically over time, that life has repeatedly found new ways to adapt and persist through catastrophes that would seem to make survival impossible. The idea of ancient civilizations on these primordial continents adds an extra layer of mystery and wonder to this already amazing story, inviting us to imagine that perhaps we are not the first to contemplate the stars, to ask questions about the nature of existence, to try to make sense of the world around us. Even if this idea turns out to be pure fantasy, even if humans are truly unique in Earth's history, the fact that we can ask these questions, that we can imagine alternative histories and think about what might have been, is itself remarkable. It speaks to something fundamental about human consciousness, our ability to transcend the immediate present, to range freely through time and space in our imagination, to consider possibilities that have never existed and may never exist. This is perhaps what makes us unique, not intelligence as such, but the particular type of consciousness we have, reflective and curious and endlessly inventive. Throughout this exploration, we have tried to balance speculation and imagination with respect for evidence and the scientific method. Science has been extraordinarily successful at uncovering the history of the Earth and the evolution of life, revealing a story that is far stranger and more wonderful than anything our ancestors imagined. We now know that the Earth is billions of years old, that continents move, that life evolved from simple beginnings to the tremendous diversity we see today, that humans are not the center of creation but one species among millions connected by common ancestry to every other living thing, These discoveries made over the last few centuries through painstaking observation and experiment have completely transformed our understanding of our place in the universe, and they have been achieved through the application of scientific thinking, careful reasoning based on evidence tested through observation and experiment. That science also requires humility, acknowledging what we do not know, admitting when the evidence is insufficient to support firm conclusions, remaining open to new ideas when new evidence emerges. The history of science is full of examples where the consensus view turned out to be wrong, where strange new phenomena were discovered that nobody had predicted, where old ideas had to be discarded in favour of better ones that explained the evidence more successfully. This is not a weakness of science, but one of its great strengths, the willingness to change in response to new information, to follow the evidence wherever it leads, even when it contradicts cherished beliefs or seems to violate common sense. When we consider questions about ancient civilizations on pre-Pangean supercontinents, we must maintain this scientific attitude, neither dismissing the idea out of hand simply because it seems unlikely, nor embracing it enthusiastically without demanding rigorous evidence. The truth is that we do not know everything about Earth's past, and we never will. There are limits to what the geological record can tell us, and some questions may be forever beyond our ability to answer. This does not mean we should stop asking questions or stop looking for evidence, but it does mean we should be comfortable with uncertainty, with admitting that some mysteries may remain unsolved, that some questions may have answers that we can imagine but cannot prove. Perhaps the most honest answer to the question of whether civilizations existed on the supercontinents before Pangea is simply that we do not know, that the evidence is insufficient to say one way or another, but that the question itself is valuable because it makes us think more deeply about the assumptions we make and the limits of what we can discover about the deep past. Rather than thinking in terms of a simple yes or no answer to whether ancient civilizations existed, perhaps we should think about organization and complexity as existing on a continuum with many different levels and types. At one end of this continuum, we have random arrangements of non-living matter, rocks and minerals, distributed according to purely physical and chemical principles, with no organization beyond what those principles produce. At the other end, we have modern human civilization, with cities and technology and art and science, with billions of individuals cooperating and competing in complex ways, with information stored and transmitted across generations through language and writing. But between these extremes, there are many intermediate levels. The simple organization of molecules into self-replicating systems that we call life, the organization of cells into multicellular organisms, the organization of organisms into ecosystems and biospheres, the social organization of animals like ants or bees or wolves, the cultural organization of early human societies before agriculture and writing. Each of these levels of organization represents something genuinely new and interesting, not just more of what came before, but a qualitatively different type of order with its own principles and properties. The organization of a modern city is not just a scaled-up version of the organization of an ant colony. Even though there are interesting parallels, it represents a different type of system with different capabilities and different dynamics. Similarly, the organization that might have existed in ancient microbial communities, if such things were more sophisticated than we currently imagine, would not be the same as human civilization, but it might still be worthy of our interest and study if we could detect evidence of it. Perhaps the real question is not whether ancient civilizations existed, which implies something like human cities and technology, but whether ancient life exhibited forms of organization that we have not yet recognized, that fall outside our current categories and assumptions. More nuanced view allows us to appreciate that the history of life on Earth has been a history of experiments in organization, with different types of systems arising at different times, some persisting for billions of years, others lasting only briefly before going extinct or being outcompeted by something new. the microbial ecosystems of the ancient Earth, which dominated for billions of years and still represent most of the diversity and biomass of life today, are organized in sophisticated ways that we are only beginning to understand, with complex chemical communication networks, with cooperation and competition between different species, with the ability to adapt to changing conditions and to persist through catastrophes. These systems are not civilizations in any sense we would recognize, but they are organized, they are complex, and they have profoundly shaped the planet we live on, creating the atmosphere we breathe and the soil that supports terrestrial life. Looking forward rather than backward, we can make predictions about the future of Earth's continents based on our understanding of plate tectonics and the patterns of past supercontinent cycles. The continents are still moving today, drifting across the surface of the Earth at rates of a few centimeters per year, slowly but inexorably changing the geography of the planet. The Atlantic Ocean is growing wider as North and South America move away from Europe and Africa, while the Pacific Ocean is shrinking as the plates around its edges are pushed down into the mantle at subduction zones. Australia is moving northward, having broken away from Antarctica millions of years ago, and will eventually collide with Southeast Asia. Africa is also moving northward, gradually closing the Mediterranean Sea, and will eventually collide with Europe, pushing up a new mountain range that might rival the Himalayas. Based on these movements and on models of how plate tectonics works, geologists have proposed several scenarios for how the continents might be arranged in the future. One scenario, called Pangea Proxima or Pangea Ultima, suggests that in about 250 million years, the continents will have come together again to form a new supercontinent, with the Atlantic Ocean having closed and the Americas colliding with Africa and Europe, while Asia remains connected to the north. Another scenario, called Amasia, suggests that instead of closing the Atlantic, the continents will drift northward and come together around the North Pole. Yet another scenario, called Eureka, proposes that both the Atlantic and the Pacific will close, with a new ocean opening up between the Americas and Africa-Europe, and the continents gathering around this new ocean. Which of these scenarios will actually occur depends on many factors that we cannot predict with certainty, because the motion of the continents is influenced by processes happening deep in the mantle that we cannot observe directly. Whatever the exact details, we can be confident that a new supercontinent will form eventually, because the cycle of supercontinent assembly and breakup has repeated multiple times in Earth's history, and will continue as long as the planet's interior remains hot enough to drive plate tectonics. This new supercontinent will have profound effects on Earth's climate, ocean circulation, and the evolution of life, just as Pangea and the earlier supercontinents did. When all the continents come together, the interior of the supercontinent will become isolated from oceanic moisture, creating vast deserts, while the concentration of continental weathering along a limited amount of coastline will affect the carbon cycle and potentially cool the climate. These changes will create new selective pressures on life, favoring some types of organisms while driving others to extinction, potentially setting off new bursts of evolution as surviving species adapt to new conditions. Thinking even further into the future, beyond the next supercontinent to the ultimate fate of the Earth itself, we must consider that our planet does not have an infinite future ahead of it. The sun is slowly getting brighter as it ages, increasing in luminosity by about 10% every billion years, and this will have profound effects on Earth's climate over geological timescales. In about 1 billion years, the sun will be bright enough that the Earth's oceans will begin to evaporate, with water vapor escaping into space and hydrogen being lost forever. Once the oceans are gone, plate tectonics will likely stop, because water plays a crucial role in lubricating the motion of tectonic plates, and without it, the crust will become locked in place. The carbon cycle will also break down as weathering and subduction cease, and carbon dioxide will gradually be lost from the atmosphere, eventually falling to levels too low to support even the hardiest plants. As the sun continues to brighten, temperatures will rise until the surface of the Earth is too hot for any life to survive, perhaps around 1.5 to 2 billion years from now, though some microbes might persist in underground environments for somewhat longer. Eventually, the Earth will become a lifeless desert world, similar to Venus today, with any remaining atmosphere slowly being stripped away by the solar wind. This will be the fate of our planet, barring some dramatic intervention by future intelligent life, whether human or otherwise, that somehow manages to move the Earth to a more distant orbit or to shield it from the Sun's increasing heat. In about 5 to 7 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, possibly engulfing the Earth entirely, or at least heating it to temperatures where the surface rocks melt, ending billions of years of geological history in a final catastrophe of fire. This long-term perspective, contemplating not just the deep past but also the distant future, reminds us that everything is temporary on a cosmic scale, that even planets have lifetimes, that the conditions that made Earth suitable for life have existed for only a portion of its history and will end long before the Sun dies. Life has flourished on Earth for perhaps 3.5 to 4 billion years, and may persist for perhaps another billion years. A remarkable run, but still only a finite period in the grand scheme of cosmic time. If intelligent civilizations existed on ancient supercontinents, they too were temporary, arising from particular conditions and eventually ending when those conditions changed or when some catastrophe overtook them. The same will be true of human civilization. We will not last forever. Either we will evolve into something else, or we will go extinct, or we will leave the Earth and spread to other worlds, transforming ourselves in ways we cannot yet imagine. The question is not whether we will end, but what we will accomplish and what traces we will leave before that ending comes. In the end, the question of whether civilizations existed on the supercontinents before Pangea may matter less than why we ask the question what it reveals about us and about how we make sense of our place in the universe. We are meaning-making creatures, constantly trying to understand the world around us, to find patterns and purpose in events that might be random or meaningless, to connect our own brief lives to something larger and more enduring. The idea of ancient civilizations, whether on Earth or on other worlds, speaks to a deep human need to feel that we are part of a larger story, that consciousness and intelligence are not accidents but somehow fundamental to the universe, that we are not alone in space or time but are connected to others who have asked the same questions and wondered about the same mysteries. Science gives us one way to explore these questions, through evidence and observation and careful reasoning, building up a picture of reality that is constrained by facts, but also wonderfully rich and complex. But science cannot answer all questions, particularly questions about meaning and purpose and value, which require philosophical and ethical reasoning, drawing on our experiences and intuitions and values to make judgments that go beyond what the evidence alone can tell us. Whether ancient civilizations existed is a scientific question, at least in principle, that could be answered if we found the right evidence. But why we care about the answer, what it would mean for our understanding of ourselves and our future, these are questions that science alone cannot resolve. They require us to think about what we value, what kind of universe we want to live in, what responsibilities we have to preserve and extend life and consciousness. Questions that each person and each generation must answer for themselves. As you drift towards sleep, contemplating these vast stretches of time and space, the ancient continents that have risen and eroded away, the forms of life that have come and gone, leaving only traces in stone, let yourself feel both the insignificance and the significance of human existence. We are insignificant in the sense that we are tiny and brief, just one species among millions, existing for a mere moment in the 4.5 billion year history of our planet, likely to be forgotten eventually, just as we have forgotten whatever strange and wonderful things might have existed in the deep past. But we are also significant because we are the part of the universe that has become conscious, that can look back through deep time and reconstruct the history of continents and life, that can ask questions about existence and meaning, that can wonder whether we are alone or part of a larger community of conscious beings scattered across space and time. There is a gift in not knowing everything, in having mysteries that remain unsolved, in being able to wonder about possibilities that we cannot prove or disprove. A universe where everything was known and explained, where there were no more questions to ask and no more discoveries to make, would be a poorer place than the universe we actually inhabit, full of unknowns and possibilities. The question of ancient civilizations on pre-Pangean supercontinents is one of these fruitful mysteries, probably unsolvable but valuable nonetheless, because it pushes us to think more deeply about the history of our planet, about the limits of what we can know, about the many different forms that life and organization might take. Even if we never find any evidence that such civilizations existed, the search itself is worthwhile, because it leads us to examine ancient rocks more carefully, to develop new techniques for detecting subtle traces of life, to think creatively about how information might be preserved across billions of years. The universe is under no obligation to make sense to us, or to satisfy our curiosity. Yet remarkably, we have discovered that much of it does make sense, that the laws of physics are comprehensible, that the history of stars and planets and life can be reconstructed through patient observation and reasoning. This is perhaps the greatest mystery of all. Why is the universe intelligible? Why does mathematics work so well for describing physical reality? Why are we able to understand anything at all about the deep past or the distant future? These questions verge on the philosophical and perhaps even the spiritual, touching on deep issues about the nature of consciousness and its relationship to the physical world. Different people will answer them differently based on their beliefs and experiences, but the fact that we can ask them, that we can wonder about our own wondering, is itself remarkable and worthy of our awe. As this long journey through deep time draws to a close, as your mind gradually releases its grip on these ideas and allows sleep to come carry with you a sense of wonder about the planet you live on, about the long strange journey it has taken from a ball of molten rock to the complex life-filled world we know today. Think about all the changes that have occurred, the continents that have assembled and broken apart, the oceans that have opened and closed, the forms of life that have emerged and gone extinct, each chapter in the story building on what came before and setting the stage for what would come after. Whether or not civilizations existed on the ancient supercontinents, we know that something remarkable has happened here, that the Earth has been transformed from a lifeless rock into a place where life flourishes, where consciousness has emerged, where a species has evolved that can look back through time and contemplate its own origins. The search for understanding our planet's history is a journey without end, because there will always be new questions to ask, new techniques to develop, new evidence to discover as we continue to explore the rocks and minerals that hold the secrets of the past. Each generation of scientists builds on the work of those who came before, refining theories, challenging assumptions, pushing the boundaries of what we know. What seems certain today may be revised tomorrow, as new discoveries force us to reconsider our interpretations and develop new models that better fit the evidence. This is the nature of science, always provisional, always open to revision, but also cumulative, with each generation adding to the collective knowledge of humanity, building a picture of reality that becomes ever more detailed and accurate, even if it is never complete. The story of the Earth before Pangea is still being written, as researchers continue to study the ancient rocks, develop new technologies for dating and analyzing them, and piece together the fragmentary evidence into coherent narratives about what the world was like billions of years ago. With each new discovery, our picture of the deep past becomes a little clearer, though it will always remain incomplete, a sketch rather than a photograph, with many details missing or uncertain. But this is enough. It has to be enough, because it is all we have. these ancient rocks and the stories they tell, these mathematical models and scientific theories that help us make sense of the evidence, these glimpses into worlds that no human has ever seen and can never see, separated from us not just by distance but by the unbridgeable gulf of deep time. And perhaps it is fitting that some mysteries remain unsolved, that we do not have answers to every question we can ask, because this reminds us that there is still more to discover, still work to be done, still reasons to keep exploring and questioning and wondering. The possibility that something unexpected might yet be found in the ancient rocks, some evidence of organization or complexity that we have not anticipated, keeps the search alive and maintains our sense of wonder about the planet we call home. Even if ancient civilizations never existed, even if the deep past holds no surprises beyond what we have already found, the fact that we can imagine such possibilities, that we can ask these questions and pursue them rigorously, speaks to something fundamental about human nature. Our curiosity and creativity and our refusal to accept simple answers when complex ones might be more interesting and more true. We began this journey by traveling backward through time, beyond recorded history, beyond the evolution of humans, beyond the formation of Pangea, back to the ancient supercontinents that existed in the deep past when the world was young and strange. We have considered what traces such ancient worlds might have left, what evidence we might find of life or organization, or even something approaching civilization. We have explored the limits of what we can know about the deep past, acknowledging that much of what happened in those distant times is lost forever, eroded away or transformed beyond recognition by the relentless processes of geology. We have thought about what it means to search for answers to questions that may be unanswerable, to wonder about possibilities that we cannot prove, and we have found value in the search itself, in the way it pushes us to think more deeply and question our assumptions. Now the circle completes as we return to the present moment, to you lying comfortably and peacefully, your mind drifting in that space between waking and sleeping, where thoughts become dreams and the boundaries between self and world begin to dissolve. You have traveled billions of years through the imagination, witnessing the formation and breakup of ancient continents, the emergence and evolution of life, the slow transformation of a dead world into a living one. You have contemplated mysteries that may never be solved, questions that will continue to puzzle and inspire generations of scientists and philosophers long after we are all gone. And now it is time to let these thoughts go, to release them into the darkness, to allow your conscious mind to rest while your unconscious mind continues its own mysterious work, processing and integrating all that you have learned, making connections and finding patterns in the rich tapestry of images and ideas that have filled your awareness during this long exploration. The Earth continues its slow dance through space, spinning on its axis to bring day and night, orbiting the sun to bring the seasons, moving through the galaxy along with all the other stars in a cosmic journey that will last for billions of years more. The continents continue their patient drift across the surface, 5 moving so slowly that no human lifetime can perceive the change, yet inexorably reshaping the face of the world over millions of years, building toward the next supercontinent that will form long after humans have either gone extinct or evolved into something we would not recognize. Life continues its endless experiment in organization and complexity, with species evolving and adapting to changing conditions, with ecosystems shifting and transforming, with the possibility always present that consciousness might emerge in new forms, that intelligence might arise again even if humanity disappears, continuing the universe's exploration of what matter can do when it organizes itself in sophisticated ways. And you, a tiny part of this vast and ancient process, a brief flowering of consciousness and awareness in the long history of matter and energy, you can rest now, knowing that you are connected to something larger than yourself, that your atoms were forged in ancient stars and will persist long after your current form has dissolved. that the water in your cells has cycled through the oceans and the atmosphere countless times over billions of years, and will continue cycling long after you are gone. You are made of earth, of the same elements that make up the ancient rocks in the deep sea and the air you breathe. And when your time comes to return to the earth, you will rejoin that great cycle, becoming part of the soil and the plants and the animals that will come after. Your atoms scattered and recombined into new forms that you cannot imagine. But that time is not now. Now is the time for rest, for sleep, for allowing your body and mind to recover and restore themselves through the mysterious processes that happen when consciousness recedes and the dreaming mind takes over. Let the questions and mysteries we have explored tonight fade into the background, becoming a gentle current beneath your awareness, rather than demanding your attention. Let the vast sweep of geological time become a lullaby. The slow rhythm of continents rising and falling, the patient work of water and wind, the eternal cycling of rock and sediment through erosion and uplift and transformation. These processes continue whether you are awake or asleep, whether you are aware of them or not, and they will continue long after you have forgotten about them, operating according to natural laws that care nothing for human concerns or human timescales. Sleep now, and let your dreams carry you wherever they will. Perhaps back to those ancient shores where the first life emerged from the primordial oceans. Perhaps forward to distant futures where new forms of organization and consciousness will look back at our time with the same curiosity and wonder that we have brought to the contemplation of the deep past. Perhaps your dreams will show you landscapes that have never existed, continents with impossible shapes, creatures that evolution has never produced, civilizations that rose on worlds that never were, the infinite creative power of the unconscious mind freed from the constraints of evidence and logic. Or perhaps your dreams will be quiet and peaceful, simple and restorative, giving your mind the rest it needs without the burden of grand visions and cosmic perspectives. In the end, all of deep time, all of the billions of years we have discussed, exist only in this moment, in the present where you are now, because the past is gone and the future has not yet come, and all we ever have is now, this eternal present moment that is constantly renewing itself, constantly becoming something new. The ancient supercontinents Pangea and Rodinia and exist now only as scattered rocks and fading memories in the stone, as patterns of atoms that once formed mountains and rivers and perhaps even organized life, now dispersed and transformed into the current configuration of the world. The future supercontinents, Pangea Proxima and Amasya, exist now only as mathematical projections, predictions based on current movements and past patterns, maps of worlds that have not yet formed and may never form if something unexpected intervenes. What matters is here and now, the reality of your existence in this present moment, the feeling of your breath moving in and out, the gradual relaxation of your body as sleep approaches, the gentle fading of awareness as consciousness releases its grip and allows you to drift into the restorative darkness of sleep. This present moment contains all of history and all of the future in potential form, because you are a product of that long history. Your existence only possible because of billions of years of evolution and geological change, and you, in turn, will influence the future through your actions and your choices, in ways large and small that ripple outward through time and space in patterns too complex to predict or even imagine. So rest now in the present moment, in the only time that truly exists, and let the past and future fade into abstraction. Interesting ideas to contemplate when you are awake, but not something you need to hold on to as you sleep. Let go of questions about ancient civilizations and pre-Pangean supercontinents. Let go of wondering about what traces we will leave and whether anyone will remember us. Let go of trying to understand or control or make sense of anything at all. Simply be here now, breathing and relaxing and allowing sleep to come in its own time, trusting that your body and mind know what they need and will take care of themselves without requiring your conscious attention or effort. and as the last threads of awareness begin to fade, as consciousness dims and the dreaming mind prepares to take over, know that you have travelled far tonight in imagination, farther than any spaceship could take you, back through billions of years to the very dawn of the Earth, forward through billions more to imagine the planet's distant future, inward into questions about consciousness and meaning that have puzzled philosophers for thousands of years. You have held vast spans of time in your mind, contemplated continents larger than any that existed today, imagined forms of life and organisation that may never have existed or may be waiting to be discovered. This is the power of human consciousness, to range freely through time and space and possibility, unconstrained by the limits of the physical body or the brief span of a single lifetime. But now it is time to set aside this power for a while, to let the conscious mind rest so that the unconscious mind can do its work of integrating and consolidating, of sorting through the day's experiences and filing them away in memory, of maintaining and repairing the body's systems and preparing you for another day of waking life. Sleep is not an absence or an ending, but a different mode of being, necessary and valuable in its own right, a time when the brain reorganizes itself and the body heals and grows. Dreams may come, strange and vivid or quiet and easily forgotten, serving purposes we do not fully understand but which seem to be essential for mental health and proper functioning. Let go now of everything you've been holding, all the questions and ideas and images that have filled your awareness during this long journey through deep time. Let them sink down into the depths of your mind, where they will continue to work beneath the surface of consciousness, making connections and generating insights that may emerge later as intuitions or sudden realizations. Trust that what is valuable will be retained, and what is not needed will be forgotten, that your mind knows how to sort and organize and preserve what matters. There is nothing more you need to do, nowhere you need to go, nothing you need to figure out or understand. Simply allow yourself to drift deeper into relaxation and peace, floating on the gentle current that carries you from waking into sleep, from effort into effortlessness, from the world of thoughts and concerns into the world of dreams and restoration. The earth turns slowly beneath you, carrying you through the night toward a new dawn that will come in its own time, bringing with it new possibilities and new questions and new opportunities to explore and wonder and learn. But that is for tomorrow. Tonight is for rest, for sleep, for the gentle darkness that embraces all living things when consciousness releases its hold and allows the body and mind to return to the deep sources from which they came. Rest now in that darkness, in that peace, in the quiet confidence that you are part of something vast and ancient and ongoing, that your brief life has meaning even if you cannot always see or articulate what that meaning is, that you are connected to everything that has ever been and everything that will ever be through the endless cycling of matter and energy that is the fundamental nature of reality. May your sleep be deep and peaceful, your dreams be kind, and your awakening be gentle when the time comes for consciousness to return. May you carry with you some small reminder of the vast perspective we have explored tonight, the sense of being part of deep time, of being connected to ancient worlds and distant futures, of being one brief but beautiful expression of the universe's ongoing exploration of what is possible. And may this perspective bring you comfort and wonder, helping you to see your life and your concerns in a larger context that makes the difficult moments more bearable and the beautiful moments more precious. Sleep well, traveller through deep time, and know that the story continues, the great adventure of Earth and life rolling forward into an unknowable but endlessly fascinating future, carrying you and all of us along on its ancient and eternal journey.